Hi. We have examined the boolean algebra. So we are examining the mathematics of logic design, which is boolean algebra. First, we set the boolean algebra axioms. Now we came to theorems. So these are the axioms. As you know, there are 4 axioms. If you know the 4 axioms, by taking the dual of them, you can get the other axioms as well. So you got to memorize only the 4 axioms. Then you can find out the other axioms by using the duality principle. So we are going to, so these are the axioms, and then these are the list of the theorems. So these theorems, axioms cannot be proved mathematically, but theorems must be proved theoretically by using these axioms or already proved theorems. When we came to that subject, maybe it is worth mentioning how many different types of proofs are there in mathematics. There are 4 of them, 4 proofs. What are they? The first one is deduction, they call it. Deduction. This is the most common one. You start, when you're talking about a theorem, there is going to be an if such and such, then this. So if these exist, then this is true. You're going to prove that. If you start from ifs by using these axioms, if you end up with this then proposition here, so that's the proof, isn't it? You're going to go step by step. From this we can get this, we can get this. At the end we end up with this. So all we have done here, step by step, is true. So the final is also true. That's deduction. The second one is a proof by contradiction. Contradiction. What is this? In Turkish, this is olmayan ergi. How this works, so you said if something true, that is true. You are assuming that that is true, we said. If you assume this opposite is true, not this, but the opposite of this proposition is true. So the opposite, true. So if you do the calculations or step by step use the axiom, if you end up with a contradiction, in this contradiction, you're going to say that if I assume that proposition, that is the result proposition, opposite is true, and then you end up with a contradiction, so my assumption is wrong. Opposite is true means itself, if I accept the opposite true, there is a contradiction. In order to get rid of from that contradiction, my assumption should be the inverse. That means opposite of the opposite. So that means the original is true. Yani yanlışın yanlışı doğrudur, değil mi? Bir şeyin yanlışının yanlış olduğunu ispatlarsan kendisi doğru olmuş oluyor gibi söyleyebilir. Bu da nereden çıkıyor derseniz Aristo mantığına kadar gidiyor. Şimdi bu zaman zaman kullanılır. Öyle çok yaygın kullanılmayan bir yöntemdir. Üçüncü yöntem, I transfer to in Turkish but come back to English again. So this is not a very common one. From time to time we could use this proof. The third mathematical proof is mathematical induction. In Turkish, indüksiyon, matematiksel indüksiyon denir. This method is used for an equation to prove that that equation is true. If this equation has got a parameter in it, let's say the n is a parameter, you prove this equation is true for n equal to 1 and 2, let's say. You've got to prove that. And then if you assume that this equation is true for n equal n, and then if you prove that if n replaced with n plus 1, it is true. You've got to prove that. You're going to assume that, and you've got to prove it. It is true for if you replace n with n plus 1. If you prove that, then you say this equation, which includes that n parameter in it, is always true. So this is a special case, once again, that you can apply this proof method. You cannot apply it to any theorems that you face with. The last one, although it is a proof method, but this is the proof something is wrong. Whatever said is wrong. To prove that is wrong, you could use this example. If this method, that is counter-example, it is called in Turkish zıt örnek, counter-example. If I prove that, so if you say that all the real numbers are even, all real numbers are even. It's not easy to prove that, but I can say this is wrong by giving a counterexample. For example, if you say that 3 is a real number, but it is not an even number, isn't it? Even number can be divided by 2. That 3 cannot be divided by 2. It's going to be 1.5. It's not. The result is not the natural number. So therefore, what I said here is not true. So I proved this by giving a counterexample. So you can use this method in order to prove what is said is wrong. So these are not very common. This is not very common as well. This is the most common one. So it is just in parentheses I explained to you the mathematical methods that we use in mathematical proofs that we use in trying to prove the theorems. These are the mathematical proof methods. So let's look at the theorem. So I'm going to do this example here. Theorem says complement element is unique. That means if you've got an element A, complement of this, we show it like that. This is unique. There cannot be more than one complement of the same element. This is what theorem says. Now I am using now proof by contradiction, saying that assume that there is another A prime element which is complement of this A. Just assume that. So that means what is said here, I am saying the opposite of it. Assume that. Not this, but this. So under this assumption, by using the axioms, I can say that A plus A prime is equal to 1. A times A prime equal to 0, because these are the axioms, isn't it? So I can, if A prime is the complement of A, so these two is true. If A double prime is the complement A, then this is also true, according to this axioms, let's say. Now I am going to do some step-by-step progress. At the end, I am going to face with a contradiction. As soon as I face with that contradiction, I am going to say what I assumed at the beginning is wrong. So the opposite of that proposition is true. So my assumption is there are two different complements of the same element A. That assumption is wrong, means it is only one. So let's do this step by step now. If I write A prime times 1, I can write that according to that axiom. Why? But there's a here, but this is A prime. So you know that complement operation is a function between S to S. So that means when you get the A prime here, A prime is also the element of S, isn't it? So this axiom tells for any element in S, there is a relation like that. So for A prime, it is true. For A, it is true. For A prime is also true because A prime is within this set S because of that relation here. Okay, I use that theorem here. Oh, that's the one. And then I can write this A double prime. This is this one, isn't it? So instead of that one, I wrote this. Okay. If you look at this and this theorem here, this axiom, sorry, here, looks similar, isn't it? A multiplied B plus C in parentheses, A prime multiplied, two things in parentheses at this, and they are summed. So if I use this distributive axiom, second one of it, dual of it, A prime times A plus A prime A double prime, I end up with. So A prime A prime A is equal to 0. I know from that. So I can write 0 plus A prime A double prime. Instead of that 0, you see here, let me change the color. So instead of that 0 here, I can write this, isn't it? So let me write it A prime. I wrote instead of that 0 here, that is, sorry, not, this is going to be multiplication, isn't it? Let me clear it and then come back again. So instead of that 0, I write A double prime. So that's the one. Plus A prime A double prime. If you look at this, this is very similar to this one, you see. Why is that? If you look at the right hand side, this A is common in two parentheses, isn't it? In here, A double prime is common in these two parentheses. So if you take this out, that means A double prime. What is left inside is this A and this A prime. So if you use this now, as if you assume that this is on the left hand side, I see this. Right hand side is going to be equal this, so that is this. So I am using the opposite of this. I have got this in my hand. Instead of this, I wrote this. Here you are. So A prime, A plus A prime, A plus A prime gives you 1. So that's the one. So this becomes 1 time A double prime. 1 multiplied with any element gives this element, isn't it? Here you are. If I use this axiom, so it's going to be A double prime. So at the beginning I had this A prime. At the end I show that A prime is equal A double prime. What it means, at the beginning I assume that there are two different complements of A. A1 was different from A double prime. So I end up with a contradiction saying that these two must be the same, equal there. And then, conclusion, my assumption is wrong. My assumption was more than one complement exists. That is wrong because of that contradiction. Opposite of it is true. Opposite means the complement is unique. So this is the proof of this first theorem. Let me clear this area now. and then come back the second one. Second theorem. Second theorem says any element added with 1 gives you 1. We've got to prove this now. Is it true or not? That's theorem. So a plus 1 is equal a plus 1 multiplied with 1. I can write that because a plus 1, consider that we are talking about this is summation operation. Summation operation is function is this, isn't it? That means at the end, you're going to end up with one element in S. So after that operation, you're going to get one element in the S. So this is just one element. So this axiom says any element multiplied with 1 gives you that element. Here you are, isn't it? So I'm using this. Okay, a plus 1. Instead of 1, I can write a plus a prime. Because it says a prime gives you 1. Okay, so if you look at this and compare this one, there are two parentheses. In the parentheses, there are one terms, they are common. These are a. Put that a out as it is here, plus multiplication of rest of the elements in parentheses. So 1 time a prime. So I use this theorem now in order to get this. How I use that? This right hand side here is this. Instead of the right hand side, I wrote this left hand side. That is the left hand side. Okay, and then any element of S multiplied with 1 gives that element, so this becomes a prime. So this is that one. A prime is equal to 1, it is in here, so that is equal to 1. So I proved that a plus 1 equal to 1. Conclusion is this: any element summed with 1 always gives you 1. A is used here for any element in S. So I proved that theorem as well. Let's come the third one. Third one, it tells us prime of 0. So another thing here, this is another theorem here. I haven't proved that theorem. Why is that? I am saying that if you proved a theorem, a relation, then the dual of this theorem is also true, isn't it? Because all the axioms has got dual axioms. By using dual axioms, I can prove that. So I am not going to prove it. How I am going to say that how I'm going to find this dual here, all you've got to do, replace plus with multiplication, multiplication with plus, 0 with 1, 1 with 0. You get this. You see here, I put a here. This plus multiplication, I have done this. 1 replace with 0, replace 0, equal 1 replace 0. So that is the dual of this here. I proved this, so dual must be, dual is also means proved. Okay, that was the third axiom that was the third axiom we proved. And I'm not going to prove this one. Maybe I need to prove this one as well. So what this says, a plus a gives you a. That's not true in our normal mathematics, isn't it? In normal mathematics, a plus a gives you 2a. There's no 2 here. So that is the true one. How I'm going to prove it? So once again, a plus a is equal a plus a multiplied with 1. So use this axiom here. And then a plus a multiplied a plus a prime. I can write this instead of 1. Here you are. I use that axiom here. And then if you look at the right hand side here, a is common, take this a out. The other elements in the parentheses are going to be multiplied here. So right hand side I am using this. Instead of this I wrote the left hand side, A at the output, and in parentheses the other elements in the other parentheses multiplied. A times A prime is equal to 0, it's here, so A 0. 0 add anything gives you that thing, so it becomes A. So that's this axiom, the final one. So I proved that A plus A equal to A. So similarly, you can say that dual of this, A times A gives you A. I leave this one to you. You could do it your own. If you are in trouble, you can look at the logic circuits notes. Although in Turkish, that notes, you could still use it because there's mathematics in there, so you can follow that. By following that, you could see the proof. So I leave this to you as well, this to you, so you do it your own. And that takes a bit longer time, so I leave this one to you as well. If you are in trouble, as I said, you can look at the logic design notes. This is another theorem that we use commonly, so let me prove this in here. What it says, A plus B prime is equal A prime B prime. Another way of saying this, A plus B element prime is equal to this, isn't it? So prime element definition is, for prime element definition, we use these two axioms. So what this axiom says, an element and its complement must be equal to 1. Otherwise, this A prime is not the complement. If it is complement, it must have that property. So if I write this now, if you say that that is the element, add this element complement. This is this, isn't it? This element complement is this. Element itself plus the complement of it must be equal to 1, it says. So I've got to prove this. If it is 1, then I'm going to say this element complement is equal to this. So how I'm going to prove it, let me do it now. A plus B let me change the order. So I can change the order, so that is associativity is changing the parentheses. So you could do it similar thing here. A prime, B prime, B is equal to what? I am on the left hand side trying to find out to end up with 1. If I can end up with this one, then I'm going to say what I said is true. That means A plus B prime is equal to this. So in here I've got this left hand side, isn't it? This one. So if I use the distributive axiom, it's A B prime. So instead of this I wrote this plus B. How I wrote this, according to this, you see, A multiplied B. Sorry, that is the one, sorry, so that's the one. Two parentheses, in each parenthesis, the common A is going to be the first element, the other elements are going to be B and C. So here are A prime and B prime. Okay. So this is equal to 1, isn't it? This axiom tells me 1 time A B prime plus B equal. So 1 multiplied anything gives you what it is multiplied. That is this one. So if you use this axiom for this one, you end up with A B prime plus B. So instead of this, I wrote this plus b then. So what I end up with, b plus b prime. So for any element a, this is true. By using this axiom, I'm going to write 1 here. So we end up with a plus 1. We already proved here as a theorem that 1 summed with any element gives you 1. So that's equal to 1. This is what I try to prove. Then conclusion is this. A plus 1 element prime is this. So this is the proof of De Morgan theorem. The dual of it is going to be like that. A b prime is equal a prime plus b prime. So if you use the dual principle, you're going to end up with this. So we proved this theorem as well, De Morgan. What is left is consensus. I'm not going to prove that one, but I'll tell you what it is. You've got an A element is common here. In one of them, you've got A. In the other one, A prime is going to be this A and A prime is multiplied with different elements, B and C. Isn't it? So those two terms, in addition BC, that means the uncommon element BC here is multiplied here. So this term is not effective. So that means if you take this off, what is left is this. So that's why it is called consensus theorem. That is consensus, agreement, same idea you've got. Then there is a consensus. So this becomes ineffective when those two comes together. So this is the theorem we use. So if you look at these theorems, some of them has got special names, some of them has no names, but in general, these are the theorems that we've got to prove. So we have shown some of the proofs here. From time to time, we will be using these theorems. Therefore, you've got to remember those theorems. Otherwise, not easy to do some of the progress. So that is the end of this video then. Let me clear it.